Thank you so much for that very kind introduction and the honor of this invitation to speak at this wonderful institution and this very distinguished audience. And I was asked to talk about science, policy, and the bridges between that. And if I have to give an assessment how we are doing in that respect, the words come to mind of Leonid Brezhnev. He was once asked whether he could capture in one word the state of the Soviet Union. And his answer was good. And then he was asked, what about two words? And his answer was not good. So here I would say, we're living in unprecedented times of scientific knowledge, global challenges that need science. But if we talk about in which way we can actually bring that scientific knowledge to bear upon these problems, it might be not that good. So I will have a mixed message today. I just want to start with a little kind of historical analog about, to which extent are we able to imagine the future, which I think is an important element that science does. And I'd like to bring to mind another anecdote. Arthur Wellesley, he was called the Iron Duke. He beat Napoleon. And by the way, the name Iron Duke was because at some point he was Prime Minister of England. And he was so unpopular that he had to put iron gates in front of his house because people would otherwise attack him. And he made this famous line in the end of his life that he says, no, in business, in war and in life, and I would say also in science, it's about guessing what's on the other side of the hill. And he took that very seriously. When he was retired, when he had guests, he would take them in a stagecoach to some new part in England. They would look at the landscape, and then the game was to guess the landscape behind the hill. Is there a wood? Is there a lake? Is there a town? And he was very good at that. Of course, you could check by going over the hill and look yourself. So I think that's a little bit what science does. It tries to imagine things that aren't there yet. So in some sense, it's tunnel vision in a positive sense. And I think this is really remarkable, and we all see this particularly with young scientists, that they're able to see things that nobody else sees by the mind's eye. And this is particularly, of course, true for everything that involves, in the end, also technology. So also if you, for instance, what is technology? There are very interesting definitions of technology. There are, I mentioned three. My favorite is one, everything that was discovered after you were born. I don't consider radio technology, but I think the internet I do. Another definition, everything that doesn't work. But actually a more honest definition is the dominant force that shapes our nature and culture. And technology is changing our lives in a way which is very hard to underestimate. So I want to give this little historical analog. So in 1939, the World's Fair opened in New York City. This was quite a big event. In total, 44 million people visited these 2 years. And this was really about showing the future. And so now we can look back and see how successful that view of the future was. And you would say it's a mixed message. For one thing, it showed the first television broadcast. In fact, Franklin Roosevelt opened the conference by speaking on television. Unfortunately, I think there were only a handful of television sets, but actually that was broadcast. So you also had the first mechanical kitchen appliances. So the modern kitchen was showed. The first robot. But there were also a big highlight of the conference was a kind of a beauty pageant of steam engines. So I would say only saw the first television. It was also basically the last steam engine train. I'm telling the story is that there was another opening by kind of a famous scientist. Actually, Albert Einstein gave a second opening speech. And that was in all possible ways a disaster. In fact, he had a very technical contraption. He talked about cosmic rays. And the cosmic rays were caught in some laboratory and then sent by telephone. And when 10 of these particles were found, he would throw a big switch, and then there should have been a big light show. But in fact, it was a massive power failure, and so totally collapsed. He was also nobody could understand him because of the very bad audio. And so the next day, the New York Times wrote that the people left the lecture of Einstein to go to something that they could applaud. So I hope I'm not in a similar situation, but it's. But he was talking about the future. And the interesting is that he didn't mention two topics. He didn't mention the nuclear physics. So this was April 39, and he didn't mention computers. Now Einstein was the first appointment of the Institute for Advanced Study, where I work, and I like to joke, since then it was downhill because we couldn't. So this is a small institution in the neighborhood of Princeton University, where he was working. Now that institution was founded in the 1930s by Abraham Flexner, and he was an interesting character because he took a few years to investigate all the scientific institutions he could find in Europe, traveled through Germany to France to England, and then he figured out that America needed an institution which was really directed towards what we would now call fundamental basic research. In fact, he was a great critic of what universities, American universities, were doing in the 1930s, was very much going to very practical applications. I know Columbia University had a course in poultry raising. And he wrote this famous essay, The Usefulness of Useless Knowledge, saying that basic research could impact life in a way which you can't even imagine. Now this was definitely true for Einstein, because in August of that same year, he actually wrote a famous letter to President Roosevelt, basically starting the Manhattan Project, starting the building of the atom bomb. So in a few months, he realized that this field of nuclear physics that he only followed tangentially certainly came, and he was convinced to write this letter. And the second thing happened. In fact, in the 1930s, he had two close colleagues. They were already mentioned in Princeton. John von Neumann, perhaps one of the smartest minds of the 20th century, and Kurt Gödel. Both were great logicians. Their passion at that time was mathematical logic. And in mathematical logic, they learned from the work from Alan Turing that you could, on paper, build machines, in fact, a universal machine, that could try to prove all possible theorems. Now, this fact that one machine is enough, von Neumann applied very soon after that, because there were the first rudimentary computers. But at that time, basically for every task, you built a new computer, just like we have household instruments. And von Neumann knew that was unnecessary, because you could make a computer do two things: calculate and program. And this is what we now call von Neumann architecture. It's in any machine you know. And he actually built the first machine according to these principles at the Institute for Advanced Study. So here you see him with then director Robert Oppenheimer in the late 40s. Now this machine is interesting. It was built out of spare parts because they couldn't afford new material, so these were war surplus. And of course it was used for weapons research. It was used to do massive calculation on the hydrogen bomb. So this small institute at that time, this is the floor plan. It had Einstein, von Neumann, and Oppenheimer, and you have to just think how that was. Einstein at that time signed, with Bertrand Russell, this notice to the world. He was the main proponent of peace and the abolishment of nuclear arms. John von Neumann was one of the coldest warriors. There's a famous story that he was asked, "Is it true, Professor von Neumann, that you feel that we have to bomb the Russians tomorrow?" He said, "No, this afternoon." Honestly. And in fact, he partly was underlying the character of Dr. Strangelove. And then you had, of course, Robert Oppenheimer, who did build the bomb, but then in some sense had second thoughts, and really tried, in some sense, to build a bridge between concrete scientific achievements and general moral principles. And in many ways, he paid a very large price for that when the security clearance was lost. So that kind of tells that if we talk about applying science to policy and scientists being in comfortable positions, this is not something that only happened in 2015. There's a long tradition. And one of my points is we should remember these previous occasions and be motivated by it and see what are the lessons we can learn for the future. By the way, that computer had a 32 by 32 memory, which is just a small fraction that my simple Casio watch has. In fact, it has these little television tubes that light it up and were kind of made a little imprint, and that was the memory chip, so to say. And von Neumann was building this for the hydrogen bomb, but he used it also for other things. So for instance, in the evening, they did the first weather prediction. So the first weather prediction was done at the Institute on January 5th, 1949. They tried to predict tomorrow's weather, and in fact, the computer was so slow, it took 48 hours. So they perfectly predicted yesterday's weather. But then soon, they get this down to 8 hours. And then von Neumann makes a remark, which is quite visionary. So he makes this remark in 1949, that understanding weather and climate will more entangle, I say with respect to my introduction, would entangle, it's the word he used, the interest of nations more than nuclear arms. And this was roughly at the height of the Cold War. So he saw, in some sense, that understanding the planet and the energy that is contained in these phenomena, which is a magnitude larger than any bomb, is more important than anything else. So in 1955, which is close to his death, he died probably from absorbing too many nuclear explosions. He was asked by the magazine Fortune to write on the theme, "Can we survive technology?" And he was asked to look forward to the year 1980, so 25 years. And it's an interesting article because the beginning is indeed about nuclear arms. And again, this was at the height of the Cold War. But that he kind of dispenses, and then he talks at length about the climate, not only in terms of natural phenomena, but he in fact was even thinking further ahead in terms of geoengineering, countries kind of impacting the climate either aggressively as a weapon or in terms of controlling phenomena. And I think this is quite interesting in some sense that at that time they had this kind of long-term view. I must say it's very difficult to find anything where John von Neumann was wrong. He was just absolutely amazing. At the same time, he launched economic game theory. You've seen it here. He launched the field of cellular automata. He did the first exploration of artificial life and using computers to simulate evolution. Really, truly a polymath as we ever had. So he ends the article on a nice note. He ends an article by saying the problems of the future of humanity can not be resolved by a single prescription, but only in reliance on day-to-day opportunistic measures and reliance on the human qualities required. Patience, flexibility, and intelligence. I find this quite remarkable, because he's such a fine mathematical mind. But he's not pointing to his equations or the computers in terms of the solution, but in a much more general case. Now, of course, we're in very different bases now. Now we have fields like climate change very much developed. We have the IPCC reports. We are removed from a single person thinking about this to massive organizations. That, of course, EASA plays a very crucial role. But I think we have still these kind of existential questions. I know Martin Rees gave a talk here, and he wrote this beautiful book, Our Final Century. I think there should have been a question mark behind that. But again, can we survive technology? And perhaps also, can technology use us to survive what is happening in the planet? And I think science plays a crucial role. And I want to say a few words in which way science can bridge that gap, both to policy and I think to the public. So let me share one anecdote I had about public engagement. I was once asked on a television program to demonstrate a little physics experiment. So there's an experiment I can recommend to all of you. So you take a little balloon, you fill it with water, and then you light a little candle under it. And it's more dramatic when you hold the balloon on top of somebody's head. The drama is there. So you're going to burn a hole in the balloon, and everybody gets wet. And then, of course, you do this, and nothing happens. So I demonstrate this. Well, it's a nice story because we all know you put a kettle on the fire and it's empty, then it gets very hot. It's full with water, and you put it on there for a minute. Of course, it's not hot. It takes a lot of energy to heat water. In fact, that explains many phenomena. So on television, I gone on about the notion of specific heat, and this is physics and everything. So I felt very good about myself. And the next morning I get an email from a very distinguished Dutch colleague. He says, well, Robert, I saw you on television. I saw the little experiment. But your explanation was totally wrong. Okay, so I think, so what mistake did I make? He said, you didn't show that experiment to demonstrate heat capacity or something. You did it for a very different reason. Why did you feel so confident to do this experiment? You knew that there wouldn't be a hole in the balloon because there was a law of nature that says that it can't happen. In fact, you did the experiment to show that you can rely on science, on the scientific method. And I think this is an important message. I think, we often, if we communicate science, we think of the latest details. But it's something to science which I think is much more fundamental. In fact, it goes right back to the beginning of the scientific revolution. Now, in terms of academies, the Royal Society was one of the first academies to establish. It had a wonderful saying, motto, nullius in verba, take nobody's word for it. And that was what they did as experiments. See with your own eyes what was going there. In fact, it's a funny story. They were royal because King Charles II gave them a charter. But in fact, we know how the king felt about these scientists. Because if you go to the diary of Samuel Pepys, he explains at that point, it was also sometimes confused with Gresham College, that's the place where they met. And he had great fun about his academicians. He said, at Gresham College, he mightily laughed at for spending time only in weighing of air. So that's what scientists did, they weighed air. So now we say we did fundamental experiments in terms of pressure of air and etc. But of course, for the king, they had just put a bit of air on a scale. It was totally useless, and the royals had great fun about these scientists. So I think very little has changed over the time. But science, of course, has some terrific qualities that are very important to us. Now, science as the belief in the ignorance of experts. That's what a quote of Richard Feynman said, science knowledge is a body of statement of varying degrees of certainty. Some most unsure, some nearly sure, but almost never absolutely certain. This is famous quote I like of Francis Crick, who discovered DNA. Any theory that can account for all the facts is wrong, because some of the facts are always wrong. You always have to start thinking. There's this anecdote that perhaps you read about. It was in the English newspapers. A woman was making an omelette, so she took an egg, broke it. It had 2 yolks. Broke another egg, 2 yolks. A third egg, 2 yolks. And then finally, after 6 eggs, the news crew was called in. There was an article of the newspaper, and it was because there's a chance of 1 in a million or 1 in 1,000 that you have 2 yolks, so 6 times in a row. That's a tremendous unlikely event. And then there was this public discussion. There were all kind of chicken and egg professors debating this issue. And perhaps a genetic manipulation, it was the same egg, or the size of the eggs was selected, and so. And then finally, one of the experts walked in the supermarket and saw boxes labeled 2 yolk eggs. So anybody who gives scientific advice should be aware of this. But let me talk a little bit more about how this kind of method of the scientific method can be applied to everyday world. And I want to say this thing what I call the knowledge paradox. Now, if you think about the way science and society are divided, I think we go into a strange situation. Every new research digs deeper. We learn more and more details about how the world works, how we work, so life and materials. And so in some sense, that scientific research becomes more complicated and moves away from the general public. On the other hand, the consequences of all that research are impacting our lives more and more. So we will get to a situation where both research is very far away, it's very complicated, but it's incredibly close by because it's impacting ours. So I think the way in which science and society will implement, I think, have this image of a kind of a fractal boundary, where knowledge is fragmented and there are little bits of expertise everywhere. And so how does the scientific community deal with it? The same about information. People talk about the University of Google. You can just go online and find everything. I sometimes have colleagues who come to me and say, did you read that paper? it's very interesting is I'm putting all kind of question marks on these issues, and then I Google myself, the author, and I find that this author not only writing very knowledgeable papers on climate change, but also talks about the so-called moon landings and the murder of John F. Kennedy. And I think, okay, so this is not a peer-reviewed result. And this is one of my colleagues had this famous saying that the problem with the global village is all the global village idiots. So we're dealing in this very fragmented, invalid sea of knowledge. And this is, I think, in particular confusing for politicians and policymakers who are kind of living in two different worlds. And I think one of the things I want to kind of emphasize here, that as scientists, we have to respect that. If you think about the world in science and politics, from some perspective, they're almost the opposite. It's almost like a particle-wave duality. Now, in science, we feel that things are universal. It's amazing, but astronomers are able to verify the laws of atoms and quantum mechanics billions of light years away. Science is precise. It wants to make statements as carefully as possible. It's totally based on rational arguments. It's about the long term. We easily go for science discoveries will be with us forever. And it's in some sense win-win. Whenever I read about a giant breakthrough from one of my colleagues, I can benefit from it because I can build upon that. Now, politics is very different. The first approximation is national or regional. Interests of countries are not necessarily parallel. A politician has to be inclusive. I can also say it has to be kind of elected. You have to include in the way you make your messages. There's a famous statement that the junior clerk in an embassy took the statement of the ambassador and said, well, I refined it and made it much more precise. To which the ambassador said, now it's totally useless because nobody will agree anymore with it. Politics have got a clear emotional basis. People make decisions not only on rational arguments. It's in some sense short term, but no politician gets be elected for life. And in some ways it's also zero sum, because one political party will the lose of another. So if we want to kind of bridge science and policy, we have to be aware that these are completely different worlds. And so we have to be careful. So I think anything that is involved in policy research has to be kind of navigate between the Scylla and Charybdis. And so there's two risks, I think, that any scientist has. One is to become kind of an activist, just go beyond what science tells you. Another is to be an isolationist and say, well, I retreat to my ivory tower and I leave the problems of the world to somebody else. Now, I'm convinced you can navigate that strait, but it's difficult. In fact, there are very many things. I live in the United States, and where you often see that politics is totally fact-free. And in fact, often, I think there's a tendency here that whenever it's a controversial issue, this is seen as being, always have to be addressed from both sides. As this cartoon shows, 2,500 scientists say we have caused global warming. I like a second opinion. It's we see certain repetitive patterns that those who feel these messages are unwelcome. You can always ask for more research, but for many cases, adding another decimal to an effect is not very helpful. So at some point also you have to indicate that although as a scientist we're always interested in more details, not all these details are equally fascinating, and perhaps we don't need them to draw some overall conclusions. We have seen recently that, certainly in the area of climate change, that certain methods of previous wars, like the tobacco wars, are being repeated. There's this famous saying, this was a beautiful book, "Doubt is our product," where an advertising company said, we are, the best way of competing with the body of facts that exists in the mind of the general public is to create more doubt instead of, having a counter argument. We see that science, the complexity of science, the details that we all love, are often turned against us. Turning complexity against science, many politicians say, well, I'm not a scientist, but it's just too complicated. I can't draw conclusions. This is a graph that was used to fight against Obamacare in the United States. And the only thing that demonstrates it's so complicated it must be wrong in some sense. No, on the other hand, it's a great dilemma because some of the messages that we bring from science are complicated. For instance, this is a beautiful graph from a wonderful book about sustainable energy that shows sustainable energy solutions as a mixed strategy, composition of various kind of energy sources. So it's not a simple message, just use A or B. Often solutions are complicated. So we have to argue for that. But how do we argue? And for scientists, I think we have to also kind of adapt, would be my point, that we live in the year 2015. So sometimes it's said in joke that when a man wants to project great authority, he wears a dress. So you see robes, and I would say this is kind of proof by intimidation. So I think the scientific community is also changing into a different mode where we not simply say, well, I'll repeat it 3 times and therefore you have to believe me, but really try to, I think, argue. The case is made that many people in the general public have now enough understanding to be kind of a proto-scientist. That is to say, follow arguments, be aware of skepticism as being a major part. And so that means that we have a different kind of engagement. A nice historical example, by the way, from the Netherlands is in the 17th century, the Dutch government instituted life insurance. It was a new thing. And the general public had to understand what was life insurance. The then Dutch Prime Minister, Johan de Witt, wrote a book about probability theory. So just think about a prime minister writing a scientific book to explain a new scientific concept to the public at large. There's a little bit of sad tale to it that, of course, that same prime minister then started a war, really changing this whole concept of life insurance. He dramatically changed the odds himself. But I think, another point I want to make is that the way we look at the academic community, I think we have to be critical. And I want to say something. The academic architecture is something also that we have to think about. Now, here you see 2 pictures of the tree of knowledge, one in the 13th century and then in the famous encyclopedia in the 18th century. At the small set of fields on the left, the third already, on the right you already see 9 pages. It's quite a gigantic tree, and this is what it looks today. So we have this incredible diversity of fields, and I feel sometimes we are a little bit like a hyperactive butcher that's kind of taking science and dividing and subdividing and subdividing. And we should think a little bit more how we engage the world. In fact, there's not only large distinctions between science, also across the world. So this is a map of the world where you see countries in terms of their surface area. Here you see a map of the world where the same countries are given in terms of the size of their scientific output. I think this is a graph from 2002. The Netherlands is conveniently in the middle. That's not just by accident, I think. And now you see Austria there being quite well represented. But you also see certain continents are completely absent. Now, if you want to make the case about stimulating scientific research in Africa, I think this graph tells it all. It's important because if you see where the impacts are of the global challenges, they are to a large extent in the global south, where the scientific infrastructure is clearly lacking. And I think there's great diversity. And we see this diversity, by the way, also in which the public opinion is engaged with scientific topics. For instance, if you ask people, are you familiar with climate change? You see that the great familiarity in the northern hemisphere. But if you see, are you acknowledging that there are human activities at the base of this, you get a very different picture, where in something the global south is in many ways more knowledgeable. So I think part of the public engagement will be also to explain to the public what the scientific infrastructure tells us. So I think we should distinguish 3 things. We should distinguish what scientists think. We should distinguish what the public think. And also what the public thinks that scientists think. And this is actually the thing I think that we can address ourselves. So for instance, climate change is a good example. In the US, I think it's 97% of climate scientists agree there are human effects. The public at large, some of the data say roughly 40%. But more important, if you ask the general public, what do you think the percentage of climate scientists is that agree with this thesis? They come in a very large number, a very small number, only 50%. So I think this is something that can change. Well, finally, a few words about building these bridges. I think it's very important and difficult, and my main point is it should be done in terms of scientific collaborations. We're living in an age where there is more collaboration than ever. This beautiful map that shows kind of the flight patterns, perhaps almost literally, where scientists are working and how they are collaborating. And you see that this is an incredibly interactive world. And I think, by the way, that academies, and I won't say too much about it today, play an important role. So I'm personally very involved in using the power in academies of science to advise and work with both at the national and at the international level. And I think there's a need to advise and make objective, authoritative, and credible, independent, peer-reviewed reports that bring the best global advice together. Now, we know it's much better to first bring the global scientific community together, synthesize a common advice, and then bring that to the global community, than do this only at the national level. And so I won't bore you with this, but the inter-academy partnership is one way in which academies of science, including the Austrian Academy, are working together at the global scale, at the European scale, and at the national scale. And so we, for instance, were very much involved with the IPCC. We took the task of reviewing the IPCC and making improvements in its processes and procedures. I was very happy to see these were implemented. And we're also doing, for instance, work in terms of global scientific integrity. There will be a book published this year, Doing Global Science, at Princeton University Press, which I think will be addressed to young scientists to be aware what it means to do this research in a global way. So kind of summarizing, I think it's very important that we spend some percentage of our time as scientists, not only to do scientific research, but also building these bridges. It's very difficult work. You have to dedicate yourself, you have to be very much aware what's happening, so to say, on the other side. But I like to make the point that if you build a bridge, you usually look at the other side. And so in the same way, I think we should stimulate policymakers and politicians to look at the world of science. I think there are many ways in which these two areas can really connect in a very deep and meaningful way. And there are lots of questions to be asked. What is the right way to collaborate? How to organize? What are the metrics that you use to communicate your scientific data? How can make sure that there's quality control? And how, perhaps most important, how do we communicate to this? But finally, perhaps my last word, I feel, and I very, very strongly about this. I said about looking ahead in the future. Well, if I would go back 50 years, and you would see what has changed in the last 50 years, I would say there are two things which are incredibly powerful. One is the enormous progress being made in scientific research. And two is the way in which we now can communicate with each other, which is totally unparalleled. So I think now these two things have to come together. And I think then we can actually solve some of the great challenges in our world. Thank you very much.